Howdy, today on Flippin Science we're looking at converting minerals to metals. So science understanding, the production of some metals requires the conversion of minerals to a form suitable for reduction. Explain with the aid of equations the methods chosen for the conversion of a mineral to a metal given sufficient information. Many of the more reactive metals, they're produced from a mineral. The mineral contains the metal chemically combined with other elements. It could be oxygen, it could be silicon, it could be aluminium, it could be a whole heap of other elements. So to produce the metal, what you need to do is remove those other elements, and then you need to reduce the metal ions of the metal that you're seeking, and that way you can produce your metal. So down here we have an example. This is bauxite, so that's the mineral that we use to get aluminium from, and here is the finalized aluminium, and you can see they're very different. Bauxite is impure aluminium oxide, so we need to remove the oxygen from the aluminium ions, and that's how we get the aluminium once we reduce those aluminium ions to aluminium metal. So here are some metal minerals and their ores. So gold and silver and platinum here. These are all very unreactive metals, so you can mine them out of the ground. They're not combined, so they're not combined with any other elements, they're just the gold, silver or platinum. But if we look at lead, zinc, iron and copper down here, we can see they're combined with different elements. And there are many different minerals that you can use to extract metals from these. So lead sulfide, zinc sulfide, iron sulfide. So here we have sulfide minerals. You can have iron oxide as well, so in that case you need to remove the oxygen atoms. Here you need to remove the sulfur atoms. There's a few steps involved in producing a metal. Some of these steps aren't needed for every single metal because the concentration of metal might be quite high in the ore, so you don't need to do some of the steps. And the method of reduction is different depending on how reactive the metal is. So you need to concentrate the mineral. In this step you remove the gangue, which is the silicate minerals that are associated with the mineral itself. So removing that gangue increases the concentration of the compound, and that's called a mineral concentrate. You then need to convert that mineral into a substance that you can reduce. So a good example of this is roasting metal sulfides in oxygen. That removes the sulfur and replaces it with oxygen oftentimes. That way you get an oxide that you can reduce a lot easier than you can the sulfide. The next step is you need to reduce the metal ions. This can be done chemically using something like carbon monoxide, which is used in iron production, and we'll look at that later. Or you can do it by electrolysis of a solution, which is what we do for copper, or electrolysis of a salt. So that's what we do for aluminium. So over here, this is a big shed where they're reducing copper solution. So the copper ions in the copper sulfate solution in these tanks is being reduced to copper metal. You then may need to refine the metal depending on the purity of what you get from the reduction step. So the copper is normally 99.999-ish% pure, so you don't need to do a refining stage for that. But for iron, for example, you need to remove carbon if you want to turn it into steel. So that's a refining step. So we're going to look at some different metal production methods so that we can see how they're reduced and the differences between them. So we're going to start with iron. So iron is produced from iron ore, and iron ore can contain many different iron minerals. In Australia, hematite and magnetite are very commonly reduced. So there's a high percentage of iron in there, and oxygen is the thing that we're removing. So the way you do this is you shove in your iron ore into the top of a blast furnace. You mix that iron ore with coke, which is carbon that's being coal really that's being cooked a little bit, and also limestone. When they're heated up, so this is done using usually gas. When they're heated up, they react together. So you get the carbon monoxide that's produced when you heat up the coke. That carbon monoxide can steal oxygens from the hematite or magnetite. So you're getting rid of these oxygen atoms, they're reacting with the carbon monoxide to produce carbon dioxide, and you're left with iron. That iron trickles down the side of the tank, and then it is collected down the bottom. So we can see here the molten iron. So here we can see those chemical reactions. So we've got our iron oxide here, it's reacting with the carbon monoxide, you're producing carbon dioxide and iron. Now this isn't balanced, but you get the idea. You're producing iron. The reductant is the carbon monoxide gas, and that's produced by the burning of the coke. So the coke burns with a bit of oxygen, limited oxygen, so you get carbon monoxide. That carbon monoxide can reduce the iron oxide to produce the iron, and you get carbon dioxide as the other product. So this is suitable for iron because iron has fairly low reactivity. So it's not particularly reactive, so you don't need a very strong reducing agent. So carbon monoxide is an intermediately strong reducing agent. It's not very strong. We'll see now in different metals you need a lot stronger reducing power in order to get your metal being produced. So let's look at zinc. So zinc is usually mined as a zinc sulfide, so sphalerite is the mineral, so zinc sulfide. You need to roast the zinc sulfide in oxygen to produce zinc oxide and sulfur dioxide. The reason for this is the zinc sulfide isn't suitable for reduction, whereas the zinc oxide is. The reason for that is zinc oxide will react with sulfuric acid to produce zinc ions in solution, and then you can reduce those zinc ions. This won't happen with the zinc sulfide. So the zinc ions in your solution you can then reduce, and we'll look at that in a second. There's often other metals mixed in with your ore. So there's a purification step of the reduction pool that gets rid of some of the extra metals that are in there. So by adding zinc powder, zinc is quite reactive, so you can reduce less reactive metal ions to their solid form, and that produces zinc ions. This is a benefit. It's good to do this because you get more zinc ions in your solution, which you can reduce, so you can make more zinc, and you get rid of impurities that would interfere with your process. So it's a win-win. The reduction step is electrolysis of a solution. So the zinc sulfate solution is electrolyzed. So we've got a lead anode and an aluminium cathode. Electricity is put in, you get reduction at the cathode. So the zinc ions are reduced to zinc metal, and the water that's present in the solution is oxidized. So oxidized at the anode, and that produces oxygen gas. So this is the key reduction step here. The zinc ions are gaining electrons to produce solid zinc. The solid zinc coats itself on the aluminium cathode, and then you just strip it off of there and melt it into ingots. So this electrolysis of a solution is suitable for zinc because zinc is reasonably reactive. So because it's more reactive than iron, we couldn't use, well, you can use carbon monoxide for zinc, but it's just not an efficient process. It's better to use this electrolysis of a salt solution. Let's have a look at aluminium now. Aluminium is produced from bauxite, which I showed you before. Bauxite is impure aluminium oxide, so we need to get rid of the oxygen. The bauxite is refined to alumina, which is pure aluminium oxide, and that alumina is mixed with another substance called cryolite, and then electrolysis occurs. In this case, it's not a solution that's electrolyzed, it's a salt. So the alumina, aluminium oxide salt, with the cryolite mix is electrolyzed to produce the aluminium. So here's the electrolysis cell. So we have these carbon anodes that are dipping in. Now here it's saying a solution of aluminium oxide and molten carbon. It's not a solution because there's no water in there. It's a mixture of aluminium oxide and cryolite, and it's heated up by the electrical process going on here generates a lot of heat. So this generates an awful lot of heat, which melts the salts. They mix together, and then we get the electrolysis happening. The carbon lining here, so it's a graphite lining of the electrolysis cell, that's the cathode, and that's where the reduction happens. As the reduction occurs, you get aluminium collecting, and that's also conductive, and that acts itself as a bit of the cathode too. So the aluminium ions get reduced to the aluminium liquid at this stage because it's quite hot, and then it's tapped off. Here are the reactions that are occurring. The aluminium ions are being reduced to aluminium, and oxygen is being produced at the anode, but this is kind of an intermediate. What's really happening is this oxygen is produced, and it's really high temperatures because you're melting a salt. So because you're doing that, that oxygen then reacts with the carbon that makes up the anodes that we saw here. So here are the carbon anodes. It reacts with those and they burn away. So you produce carbon dioxide and carbon monoxide. And replacing those anodes regularly is a bit expensive. The reason why we have to do this with aluminium is very reactive. So because it's very reactive, we need to electrolyze the molten salt. If we did this in solution, we would electrolyze, and the water would be reacting, not the aluminium ions, because it takes less energy to reduce water than it does to reduce aluminium ions. So you wouldn't get your reaction happening. The other thing is aluminium oxide doesn't really dissolve in water, so you won't even get you won't even produce a solution if you mix the aluminium oxide and water. Today on Flipping Science, we looked at how you can produce metals from their minerals. That's it for Flipping Science today. See ya.